Okay, here's a problem that tests both competencies in the linear combination section. Change the following linear combination problem into a problem of the form LSAB. Remember, LS is linear system, A is the coefficient matrix, B is the vector of constants. And find the vector form of the solution. So you can go ahead and pause this video, work the problem, and see if your answer agrees with mine. I'll give you the answer in a moment. Okay, let's talk about the solution. Okay. We want to isolate the variables. The variables are x, y, z, u, and v. Okay. So that means that my n is 5. You should always be asking yourself, what is n, what is r? Because that tells you something about the characteristics of the solution. All right, so I want to do these variables one by one. I want to get this as a linear combination of vectors. Then it's easy to convert it into a linear system. All right, so here I have x. Sorry, I'm going to need more room. X, now we want to go component by component. The first component has x's. That's going to go in the first component here. Second component has x's that are going to go in the second component. Third component has x's go here. So right here I have 2. Actually, I can go ahead and write that my 2 minus 1, 2 here. Any other x's? Here's an x. 3 times 2x. That's going to give me plus 6 here. Right? This plus 6 here means plus 6x. Comes from this vector. Okay. No other x's here. Here's another x. There's a 1x in the first component, but that's on the right-hand side, so I need to make this to be a minus 1 because I'm bringing the 1 on the right-hand side over to the left-hand side. So that's giving me all of my x's. Let's look for y's. Okay. This is like Where's Waldo? All right, no y's here, no y's here. Let's see. Here I'm going to have y. Let me bring the 7 inside. So that's going to be 7 times 0 is still 0. 7 times 2 is 14. 7 times 4 is 28. Okay, and here's a y here, 3y. So I'm going to get a plus 3 here. No y's here, no y's here. Here's a y, which is a 1 on the right-hand side. Bring it over to the left-hand side, gives me a minus 1. Okay, so that finishes off the y's. Let's look next for z's. All right, z. No z's here, no z's here, no z's here. 3z here. And then there's no other z's here. No z's here, no z's here. There's a z in the bottom that's on the right-hand side. Pull it over, gives me a minus 1. And then there aren't any z's here, so we just put a 0. Okay, then I get u's. All right, no u's, no u's, no u's, no u's. Here's u's. This is going to give me u times 16, 10, 8. And then nothing else, so we close that off. And then v's, the only v I have is this one here, so this is going to be v times 5, 12, 13. Am I done? The answer is no. I have my vector of constants. All right, so here I have a constant here, and no constants here, 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 no constants here. Here's a constant here. So I have 2 constant vectors, this one and this one. Now, since I'm putting my variables on the left-hand side, I'm going to put my constants on the right-hand side. So I'm going to keep this one over here. That's going to be minus 1, minus 2, minus 3. And then I'm bringing this 1, 9, 2 over to the other side, so that gives me another minus 1, minus 9, minus 2. All right, put this all together, and I get my equation in vector form. So here I'm going to have x times, we just do 1 minus 1, 8 plus y times 0, let's see, 17 minus 1, 16, 28, plus z times 3, 0, minus 1, plus u times 16, 10, 8, plus v times 15, 5, 12, 13. is equal to -2, -11, and -5. All right, now, I asked what the question, what n was. So n is 5, that's the number of variables. What about r? R is the number of basic variables. Well, I can't tell exactly what r is, but I can tell that r is less than or equal to 3. R is less than or equal to 3. Why? Because I only have 3 rows in this system of equations, and the value of r, which is the number of basic variables, has to be less than or equal to the number of rows. Now there could be fewer. These could turn out to be linearly dependent. I mean, it could turn out that the RREF has a 0 row. I don't know that yet, but at least I know that r is less than or equal to 3. Right? So that tells me that I have to have free variables. So if the equations are consistent, then free variables will exist. So at this point, I can tell that either there are no solutions, so there are either no solutions, and that would be inconsistent, or infinitely many solutions. Okay. Now you didn't need to do this to solve the problem. I'm just trying to give you some background to know that when you're working the problem, if you don't get something like this, you know that you've done something wrong. And this kind of thought process should always go through your head. What kind of properties is the solution going to have? So it's possible that this system is inconsistent, but if it's not inconsistent, then it's going to have infinitely many solutions. And it has at least 2 free variables. At least 2 free variables. Okay. All right, so let's go on. From this vector form, I can certainly write down my coefficient vector A and my constant coefficient matrix A and my constant vector B. So here I have A equals 1 minus 1, 8, 0, 16, 28. And then I have 3, 0, minus 1. Then I have 16, 10, 8. Then I have 5, 12, 13. And then I have, all right, so that's the end of my A. Then my B, my constant vector, is equal to minus 2, minus 11, and minus 5. All right, so I can just use software to REF. With a big one like this, I would only expect you to use software to do the RF for this one. So I'm going to pause and do the RF and get back to you. All right, so here's the REF showing down here. And now I need to use this to get my solution as a linear combination of vectors. All right, now we know that our solution is going to have 5 variables. X, so here let me just get some more space. I won't need to refer to the stuff above. So the solution my solution is going to have 5 variables: x, y, z, w, x, y, z, u, and v. No w. All right. Now, how do you do this? This is the x column. This is the y column. This is the z column. This is the u column. This is the w column. This is the constant column. So let me look at these equations one by one. Remember that these columns correspond to different variables. All right, so let's look at the first equation here. This first equation is telling me that x is x plus minus 50 over 121u plus minus 76 over 121v is equal to 163 over 121. All right, so that's the value of x. Put that in your mind. X plus minus 50 over 121u plus minus 76 over 121v is equal to 163 over 121. So what's the constant associated with x? The constant associated with x is 163 over 121. And that's going to be the contribution from the constant vector. All right. Now, what about the u contribution? Well, here I had x plus minus 50 over 121u. If I bring that minus 50 over 121u to the other side, I'm going to get a u times plus 50 over 121. Right? Similarly, here I have x minus 76 over 121v equals the constant term. If I bring that to the other side, I'm going to get a v times plus 76 over 121. Okay? So that's how you read off the first line of these three equations here. Second line, y. Then here I have plus u times 145 over 242. Bring it over to the other side, that becomes a minus 145 over 242. Plus 86 over 121. Bring it to the other side, it becomes a minus 86 over 121. Equals this constant term minus 73 over 121. That gives me a minus 73 over 121 here. Now, unfortunately, I didn't write this very well, so let me erase these and make them line up more nicely. Because what I just wrote is the y's, so let's go ahead and take these out. That's my y row, so let me just make very clear that that's my y row. All right, let's do my z row. Not 0, but z row. Okay, what does the z row tell me? Z row tells me z plus 6062 over 121u. That's 662 over 121 on the other side becomes a minus 662 over 121. Plus 227 over 121 on the other side, that becomes a minus 227 over 121. And that's equal to minus 135 over 121. That becomes a minus 135 over 121 as my constant contribution. All right, now am I done? The answer is no. I've got two more variables. I have u and I have v. Now u and v were arbitrary. Those were my free variables. Since they're arbitrary, their constant term doesn't contribute, so I get 0 and 0. The u term, here I just put u is equal to, this is just telling me u equals 0, u, and then v equals v. All right. That seems kind of ridiculous or redundant, but it does express the solution set as a linear combination of vectors, which has theoretical importance. All right. So I have all of my variables as a linear combination of vectors where u and v, the free variables, are arbitrary. All right, so you can make up your own examples in practice with this. You may be able to check your answers with Wolfram Alpha. So that's it.